Okay, so I'm trying to understand what a Julia set is. From what I remember, it has something to do with fractals and complex numbers. But I'm not entirely sure how it works or why it's important. Let me try to piece together what I know. First, I think Julia sets are related to the Mandelbrot set. Both are named after mathematicians, but their definitions might be a bit different. The Mandelbrot set is defined using complex numbers and iterations of functions, right? And I remember that it's connected, which makes it look like a big, connected shape with intricate details. Now, Julia sets are probably also associated with complex dynamics, where you iterate functions on the complex plane. So maybe each point in the complex plane can be considered part of a set itself, called the Julia set, and then there's another set, maybe the Fatou set, which is its complement. That makes sense because sometimes points behave differently under iteration depending on whether they're in one set or the other. I think the function used for this iteration is often something like f, z, equals za superscript 2 plus c, where c is a complex constant. So each point z is transformed by squaring it and adding another complex number c. If I apply this repeatedly, what happens? The behavior of the sequence depends on where z starts. If I start with some initial value for z, I'll generate a sequence, za euro equals z, then za equals f, za euro, za equals f, za, and so on. Now, whether these points stay bounded or escape to infinity as we iterate them determines if the initial point is in the Julia set or not. Wait, does that mean if after many iterations the magnitude of z doesn't get too big, then the point is part of the Julia set? Or is it about whether the orbit remains bounded or not? I remember something about escape time algorithms being used to draw images of Julia sets. You pick a threshold, say 2, and if the absolute value of z ever exceeds this threshold during iteration, you stop and color the point based on how quickly it escaped. But then there's also another set called the Fatou set, where points have stable behavior under iteration. So maybe points in the Julia set are chaotic or sensitive to initial conditions because they're highly dependent on the function and the starting point, whereas points in the Fatou set might either converge to a fixed point or cycle between several values. I'm also trying to remember if there's a condition that makes the Julia set connected. I think it has something to do with whether C is inside the Mandelbrot set. If C is inside the Mandelbrot, maybe the Julia set is connected, otherwise, it might be disconnected, like in the case of the filled Julia set being Cantor sets of intervals. So putting this together, a Julia set is a fractal created by iterating a function on the complex plane, and depending on whether points escape to infinity or not under iteration, they're part of different sets. The connection to the Mandelbrot set probably comes from the fact that the same function defines both sets, but with different starting conditions. I should also think about why this is interesting. Julia sets are examples of fractals, which have self-similar patterns at various scales. They're not just ordinary geometric shapes, they exhibit infinite complexity and detail even when zoomed in. This makes them fascinating for mathematicians to study because of their complex behavior and the variety of shapes they can produce. I wonder how exactly points are colored on a Julia set image. Is it based on the number of iterations before escape, or is there more to it? I think it's probably related to the iteration count and maybe the distribution around certain areas of the complex plane. Another thought, perhaps Julia sets have similarities with other types of attractors in dynamical systems, like strange attractors, but they're specifically defined using complex quadratic polynomials. This makes them unique compared to other attractors that might come from different functions or spaces. I'm trying to remember if there are any specific properties of Julia sets that make them so visually appealing. I think their connectedness and the presence of infinitely detailed structures contribute to their beauty in fractal art. Also, because they're defined using complex numbers and iterative processes, they have a lot in common with other recursive mathematical constructs. In summary, a Julia set is a fractal generated by iterating a function f, z, equals za superscript 2 plus c on the complex plane. Depending on whether the iterations remain bounded or escape to infinity, points belong to different sets either part of the filled-Julia set, which might be disconnected if C is outside the Mandelbrot set, or the Julia set itself, where the behavior is chaotic and sensitive to initial conditions. The connection to the Mandelbrot set suggests that properties like connectedness depend on whether C is inside it. This leads to a lot of interesting behaviors and visual complexity in the resulting images. A Julia set is a mathematical set derived from complex dynamics, typically constructed using the function f z equals z2 plus c backslash, where c is a complex constant. The behavior of points under iteration of this function determines their inclusion in the Julia set or its complement. Here's a structured explanation. One function and iteration, the function used is f z equals z2 plus c backslash. Starting with an initial point z underscore 0 backslash, we generate a sequence z underscore 1, z underscore 2, backslash by repeatedly applying the function. To behavior of points, each initial point in the complex plane is either in the filled Julia set, points remain bounded under iteration, or part of the Julia set, points exhibit chaotic behavior. 3 Mandelbrot set connection, the Julia sets are closely related to the Mandelbrot set, which defines c backslash. Points inside the Mandelbrot set often lead to connected Julia sets, while points outside may result in disconnected sets. For fractal nature and coloring, the images of Julia sets use coloring based on how quickly points escape to infinity, escape time algorithms. This results in intricate, infinitely detailed patterns. 5 Connectedness, the filled Julia set is connected if c is inside the Mandelbrot set, while being disconnected otherwise. 6 Dynamical system similarity, unlike strange attractors from other systems, Julia sets are defined by their recursive nature under complex iteration. 7 Visual appeal and complexity, their intricate structures contribute to visual appeal, showcasing infinite complexity and detail. In essence, a Julia set is a fractal characterized by chaotic behavior under function iteration, with unique connections to the Mandelbrot set and a variety of visually striking patterns.